Welcome back, focused learners, to today's Explainer. As developers and technologists, it is so incredibly easy to obsess over the visible layer of our apps, right? The slick frameworks, the APIs, writing that perfectly clean code. But the real power, the actual engine that's quietly running our entire digital civilization, well, it's pretty much invisible. Behind literally every application you use, there is this foundational system that does way, way more than just store a bunch of ones and zeros. It essentially organizes reality. Think about it. The flights you book, the money you wire across the globe, even the high-definition video you are streaming right this very second. All of it runs on an underlying architecture that dictates structure, power, and ultimate control. Okay, let's dive into this. The central question we're exploring today is actually incredibly profound. How exactly do we organize reality so that machines can understand it? And look, this isn't just some dry technical hurdle. It is a massive story of human ambition, one that bridges the gap between mechanical weaving looms and modern artificial intelligence. So to really understand how we got here, we're going to trace 5 massive evolutionary leaps. We'll start with the invisible architecture, move into the mechanical dawn, then the relational revolution, check out the web-scale fracture, and finally land on the modern data paradigm. All right, part 1, the invisible architecture, organizing reality. Through every single era of computing, the core goal has never really changed. We want to capture reality as accurately as possible to drive automated decisions. What has evolved, though, is the sheer, mind-boggling scale of it all. By 2025, the global data sphere is projected to hit 75 zettabytes. Just to put that into perspective, that's 175 trillion gigabytes. And when this invisible architecture fails, well, just look at the massive US air travel crisis in 2023. A single corrupted database file literally grounded flights and stopped the world. But to understand this massive ocean of data we have today, we actually have to look back to an era of intense physical constraints. Which brings us to part 2, the mechanical dawn, and the era of physical constraints. In the very beginning, data was physical. It was fragile and it was heavily constrained. Back in 1801, the Jacquard loom actually automated weaving using punched cards, which was essentially physical memory. Fast forward to 1890, and Herman Hollerith used similar cards to literally save the US Census from taking a full decade to count, which, fun fact, ended up birthing IBM. But even then, data still had to be searched sequentially on physical tapes. It wasn't until 1963 that Charles Bachman invented a way for data records to point to one another, kind of like a web, which set the stage for a massive, massive leap the very next year. Enter American Airlines, who partnered up with IBM to build the legendary Sabre system. Driven by the airline's president, C.R. Smith, this massive undertaking required an unbelievable $40 million investment. In today's money, that's nearly $400 million. Powered by 2 giant IBM 7090 mainframes, Sabre spanned the entire continent, processing 83,000 phone calls a day, and it dropped booking times from agonizing hours to mere seconds. But Sabre taught the tech industry a really critical, if somewhat dark, lesson. The query layer is absolutely not neutral. Following airline deregulation in the 1980s, American Airlines actually programmed Sabre with a deliberate bias. They ensured their own flights appeared first on travel agent screens, completely burying their competitors on page 2. And while congressional investigations ultimately had to step in with new regulations, the historical reality was cemented right then and there. Databases are not just passive storage, they are highly competitive weapons. Whoever controls the database, for sure, controls the marketplace. Let's move on to part 3, the relational revolution, decoupling storage. Now, what's really interesting about this slide is how it highlights a massive bottleneck. As those early systems grew, if a developer changed just one data structure, thousands of dependent programs instantly broke because they relied on these incredibly rigid physical hardware pointers. But then, in 1970, an IBM mathematician named Edgar F. Codd completely changed the game. He introduced the relational model. He completely decoupled logical data from physical storage and introduced dynamic tables. So instead of having to tell the machine exactly how to navigate through the hardware to find the data, you simply described what you wanted. And you described what you wanted using this exact syntax. Developed by Donald Chamberlain and Raymond Boyce for IBM's System R project, this was initially called SQL and later just SQL. It was honestly a brilliant sleight of hand. It took incredibly complex mathematical set theory and essentially disguised it as straightforward, everyday English. Suddenly, you could search millions of records in seconds using a language that pretty much anyone could read. A real game changer. Naturally, this sparked a fierce decade-long race. On one side, you had UC Berkeley's Project Ingress, proving the model worked in academia, while on the other, IBM's System R was acting as a top-secret corporate skunkworks. But here's the kicker. IBM hesitated. They were terrified this new tech would kill their existing, highly profitable database revenue. Seeing this massive opening, a young Larry Ellison launched Oracle in 1979 on much cheaper computers, totally beating IBM to market. And by 1986, SQL had become the undisputed universal standard across the board. Let's move to and see how this builds in Part 4, the web-scale fracture and the dawn of the NoSQL era. By the late 90s, developers were hitting a massive brick wall. Their code was using these rich, complex objects, but databases were still stubbornly stuck using rigid tables. And then, the World Wide Web arrived. It brought a scale of pure chaos that single, centralized relational databases simply couldn't survive. Companies like Google and Amazon quickly realized there was absolutely no way they could index the entire web on a single, perfect server. So they forced a radical trade-off. They completely abandoned ACID, that perfect bulletproof consistency of the relational world, and instead embraced Base. They accepted eventual consistency in exchange for the ability to scale horizontally across thousands and thousands of cheap commodity servers. This massive fracture birthed the open-source NoSQL movement, giving us these highly specialized paradigms custom-tailored for the Wild West of the web. We got document stores like MongoDB for handling super flexible JSON objects. We saw wide-column databases like Cassandra, built specifically for absorbing massive, planetary-scale write loads. Key-value stores like Redis popped up for sub-millisecond caching, and graph databases like Neo4j emerged to map incredibly complex, web-like relationships. Just like that, the one-size-fits-all database era was officially over. Which brings us to today, in Part 5, the modern data paradigm, polyglot and AI. Because today, developers are no longer just writing basic queries. They've become data architects practicing what's known as polyglot persistence. Basically, a single modern application now orchestrates multiple specialized engines all at the same time. You might rely on Postgres' secure financial ledgers, fire up Redis for lightning-fast caching, and seamlessly integrate Elastic for text retrieval. And the best part, the cloud makes this entire complex infrastructure completely invisible, just auto-scaling quietly in the background. Now, the massive generative AI boom has forced our most recent evolutionary leap, vector embeddings. We are no longer just indexing boring, tabular facts, we are literally indexing meaning. Vector databases store these high-dimensional mathematical representations of text, images, and sound. But calculating the mathematical distance between concepts in real time, they are the secret sauce powering semantic search and retrieval-augmented generation for modern AI. And this brilliantly illustrates how data architecture constantly adapts to match human ambition. But, managing the technology itself isn't enough anymore. We also have to manage human and organizational scale. Let's face it, centralized data teams almost always become a massive bottleneck. The modern solution to this is an organizational framework called data mesh, which revolves around something called data products. Instead of hoarding everything centrally, data is treated as an autonomous, self-serve asset. It's owned by the specific business team that actually creates it, and it's securely published through explicit contracts for anyone else in the company to just grab and use. So what does this all mean? The crucial takeaway is this. From Jacquard's physical punched cards all the way to semantic vector spaces that traverse the entirety of human knowledge, the database has essentially evolved into the central nervous system of our digital civilization. But as we stand right now on the brink of mind-bending tech like quantum storage and edge computing, we are left with one final provocative thought to chew on. We have clearly mastered how to organize information, but how do we continue to build systems that can truly scale with the relentless, unstoppable pace of human ambition? Thank you so much for exploring this invisible architecture with us today in this explainer. Keep learning and always keep asking those big questions.